All right, so in part one, we talked about the relationship between the derivative of a function and what intervals on which that function is increasing or decreasing. We also talked about the relationship between maximum and minimum values. So I want to get a little deeper into that maximum and minimum value idea. There are a couple different kinds of maximum and minimum values. There are what we call local maximum or minimum values, and we're going to group that all together with a term that we call local extrema. And then there are what we call absolute maximum and minimum values. We're going to be sticking to the concept of local extrema in this section, but we'll deal with absolute extrema later in chapter 3. So how do we define these local extrema? Well, suppose we have a function, f of x, and it's defined on some open interval containing that some number c. We say that f of c is a local maximum if f of c is greater than or equal to f of x for all x near c. So here's what that means. Suppose we have a function, and we're looking at a graph of that function. So here's y and here's x. Here's some value c, right? We're looking at a small little interval kind of surrounding c on the x-axis. Now, my function is going to do something like this. This is just an example. Okay, so I missed it a little bit, but let's say if I plug c into my function, I get this point. So this on the y-axis would be f of c. Now notice in my picture here, that's the lowest point within. I made my interval too big actually. I'm gonna make a smaller interval. It's the smallest point that I get from any x value that I could plug in from that little interval surrounding c. Right? If I pick any other number within this small interval right here, plug it into my function, I'll get points that are higher than this one. So in this case, I actually gave you an example of a minimum, not a maximum. F of c is less than or equal to f of x for all of the values of x that are near c. Now, if I get far enough away from c, I can plug in other values of x that are even lower than this one. But for a local maximum or local minimum value, it only matters what's happening right near c on this x-axis, okay? So a local maximum means that f of c is greater than or equal to f of x for all x near c. Local minimum is the same thing, but with the inequality sign reversed. F of c would be the smallest value that we get in that interval. And whether we're dealing with a local maximum or local minimum value, we call either of those a local extremum, or plural would be a local extrema. Okay? We also sometimes just say local extreme that's also correct. All right, so based on the discussion that we had at the beginning of this section, these local extreme values will only ever occur at a place where either the derivative of my function is equal to 0, or if the derivative does not exist. However, that can only be the case if the function is defined at that value. So f of c has to exist, but f prime would not. That's the other way we can get a critical value. So those are the things that we call critical values. Values of c for which either one of these occur, and those are where local extremes can occur, local extrema. So let's do an example where we're trying to find critical values. Notice this is going to feel like pretty much the same process as finding partition numbers. The only difference is that for a partition number, the function does not have to be defined if the derivative fails to exist at that number c, whereas for critical values, the number does have to be in the domain of f, even if it's not in the domain of its derivative. So starting here, finding the critical values, we first take the derivative. Y prime is equal to 3x squared plus 30x plus 27. Okay, since it's a polynomial, this derivative is defined everywhere. So we're not going to get any critical values from this second part of that definition. We're only going to get them from where the derivative is equal to 0. So now we need to find where those values are. Okay, so I'm going to set this equal to 0 and then try to solve it. It's a quadratic, so I can factor it. First, I would want to factor the 3 out. That leaves me with x squared plus 10x plus 9. And that is easy to factor. It's equal to x plus 1 times x plus 9. So that means that the two values that I get from this are x equals -1 and -9 by setting each of these factors equal to 0 and solving for x. These are places where my derivative fails to my derivative is equal to 0, which makes them critical points or critical values. Those are the only critical values that I'm getting out of this example. Let's try a harder one. Find the critical values of y equals e to the 2x over x minus 4 squared. So to take the derivative of this function, I'm going to need to use the quotient rule. So the quotient rule says I take the bottom function, multiply it by the derivative of the top function. And from my chain rule or my generalized exponential rule, the derivative of e to the 2x is 2e to the 2x. So again, remember that thing gets multiplied to the bottom function, x minus 4 squared. And then I subtract from that the top function times the derivative of the bottom function. So the top function is going to stay put, e to the 2x. My bottom function, I use the chain rule on because it's a composite function. So if I take the derivative of the outside, I would use the power rule. The 2 is going to come down. I'm going to bring that 2 all the way out here, though, just because I kind of prefer to see it written that way. And then I'm left with x minus 4 to the power of 1 now, which I'm not going to bother writing the power of 1. And then the chain rule says I would multiply by the derivative of the function on the inside. But x minus 4 has a derivative of just 1, and multiplying by 1 would not change anything. So I'm going to leave that alone. I'm going to take that, and then from my quotient rule, I put that whole thing over the denominator squared. Well, the denominator is already being squared. So if I square something that's being squared, it is now being raised to the 4th power. Okay? Looking at what's left here, I see an x minus 4 occurring in all of the factors that I see in this entire expression. So I can cancel an x minus 4 from each one of these. That's going to become a 3rd power there. In addition to that, I have this 2e to the 2x showing up in both of my numerator terms. I can factor that out, 2e to the 2x. Okay, that would leave me with just this x minus 4 here. Let's go like this. That x minus 4 minus, now the only thing that's left here after I factored 2e to the 2x out is just 1, so it's minus 1. Over x minus 4 cubed. But I can simplify that. X minus 4 minus 1 is the same as x minus 5. So this becomes 2e to the 2x times x minus 5 over x minus 4 cubed. Okay? Now, I need to find critical values. So again, that's going to be where this derivative either fails to exist, but is still defined for the original function, or where the derivative is equal to 0. And with a function that's represented like a quotient, you get both of those things. So for example, this will equal 0 only when my numerator is equal to 0 and my denominator is not. So my numerator is equal to 0 when? Well, I have a product. I can use my zero product property, but the exponential function is never equal to 0. It's only positive. So 2e to the 2x has no chance of being equal to 0, which means only this x minus 5 could be equal to 0. That implies that x is equal to 5. That's the only way I can get a 0 out of this. Is this derivative not defined anywhere? It's not defined when x is equal to 4. However, 4 is not a critical value for this problem. Because again, coming up here, critical values can occur either when f prime is equal to 0 or when f prime does not exist at c, but c is still in the domain of the original function. So yes, it's true, the derivative is not defined at 4, but the original function was also not defined at 4. So 4 was not in the domain of the original function, which means it cannot be a critical value at all. X equals 5 is the only critical value I get from this function. Okay? All right. So the concepts we've talked about up until this point lead to something that we call the first derivative test. And it's a test for extrema, using those critical numbers. So here's how the test works. Suppose f is continuous on some interval containing the critical value x equals c. And suppose also that f is differentiable near c. The c is missing here. And on both sides, I see, differentiable near and on both sides of x equals c. Then f of c satisfies one of the following. F of c is either a local maximum or a local minimum or neither, but we know how to identify which case is which. If f prime of x changes sign from positive to negative at x equals c, then we have a local maximum. And here's why. If it's going from positive, that would indicate that my function is increasing. Then to negative, that indicates that my function is decreasing away from it. Then we have this maximum value right there. The flip side of that, if f prime of x changes from negative to positive at x equals c, we have a local minimum. Negative means that my original function is decreasing. If f prime is positive, we're increasing. So it creates a lowest point when that happens. Okay? And then if we do not see a sign change at all at f prime of c, then we have neither a local or minimum or maximum. And that's because of that one example that we saw before. Here is something where I have a horizontal tangent right here, but we go from increasing to increasing. So there's no sign change in our derivative, and therefore we would not have a local extreme value right there. So here's what we're going to do for the first derivative test. We're going to use this to determine where certain functions have minimum and maximum values. Now I gave kind of this 4-step process here, but this process is pretty much the same as what we did with our partition numbers to find where a function is increasing or decreasing. We're just adding the first derivative test into that process to also identify extreme values. So it'll be a little better if we just jump to the example and see how this works. I want to determine the local extrema of this function. F of x equals x cubed minus 6x squared plus 9x plus 2. So what we would do first is determine the domain of f, just like we did in those other examples. It's a polynomial. For any polynomial, the domain is all real numbers. So there's not really much information coming out of that. Next, what we want to do is find the critical values. Okay, so in fact, a little bit more generally, we want to find the partition numbers. Now, in this case, the partition numbers and the critical values are the same thing, because the only difference between a critical value and a partition number is a partition number could be a place where the function is not differentiable and the function is also not defined there. So that would be a discontinuity. Critical values cannot occur at discontinuities, but they can occur where a function fails to be differentiable. That's kind of a subtle difference, and not a lot of examples will actually see the difference between those, but it's possible that, you get a partition number that's not a critical value. In this case, I'm going to find all partition numbers. That means all places where the derivative either equals 0 or is undefined. So we take our derivative, f prime of x is equal to 3x squared minus 12x plus 9. Hopefully by this point you're able to take derivatives of polynomials as quickly as this. You should have had enough practice with this by now. We want to see where is this equal to 0. This is going to be defined everywhere. So there's no way we're going to get one of those critical values where f prime doesn't exist. We really only are going to see critical values or partition numbers where it's equal to 0. So let's factor this. Pull a 3 out first. 3 times x squared minus 4x plus 3 equals 0, which is the same as 3 times x minus 1, x minus 3. That's how that quadratic would factor. And this implies that x is either equal to 1 or 3. Those are the only values I get out of solving this equation. I use those to partition up my number line. So 1, 3. And we pick some test values, just like we did before. I want to know, where is this function increasing, where is it decreasing, because that information is necessary to use the first derivative test. So start by picking test values. To the left of x equals 1, I could use x equals 0. If I plug a 0 into this version of my derivative, which notice it seems to be easiest when we plug that into our factored form of our derivative, I'll have 3 times negative 1 times negative 3, or positive times negative, which is positive. F prime is positive there. Okay? Now, if I pick a number between 1 and 3, like 2, I use that as a test point. Plug it in. 2 minus 1 is positive 1. 2 minus 3 is negative 1. So I have positive times negative, which is negative. F prime would be negative. Now I need to pick something larger than 3. Doesn't matter how much bigger. I can make it 4. I can make it a billion. It doesn't really matter. Just needs to be anything bigger than 3. But 4 minus 1 is positive. 4 minus 3 is positive. So I have positive. The product will be positive. F prime is greater than 0. Okay? So here's what we're seeing. We're seeing a change from positive to negative, and then a change from negative to positive. If we go from positive to negative, that means our function is going from increasing to decreasing. And if we're going from negative to positive, that means we are going from decreasing to increasing. So our first derivative test says that we have a local maximum of... Now, here's the next thing. We need to know what this is equal to exactly. Because notice it says determine the local extrema of this function as well as where they occur. 1 is where this local maximum occurs. But what it is equal to is whatever I get from plugging 1 into this function. So let's do this mentally. If I plug 1 into, sorry, not the derivative, but the original function up here. Okay, I'm going to get 1, so let's actually do that. F of 1 is equal to 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2. What's that equal to? So that's 1 minus 6, so negative 5, plus 9, positive 4, plus 2, 6. So we have a local max of 6 at x equals 1. So that's the actual maximum value, and this is where it occurs. We also have a local minimum, so a local minimum of what? Well, we have to figure it out, but we know where it occurs. It's at x equals 3 from our sign chart in the first derivative test. We have to plug 3 not into the derivative because we already know what happens there. It equals 0, but we plug it into the original function because that's the thing we're trying to maximize or minimize. This is equal to 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2. Okay? 3 cubed is 27, and 9 times 3 is also 27. So 27 plus 27 is 54. Now over here, 3 squared is 9, times 6 is also 54, but I'm subtracting those. So I have 54 minus 54. That's 0 plus 2. I get a 2 from that. So local minimum of 2. These are my answers for that. Okay? So one example of using the first derivative test under our belts. Let's take a look at another example. For this one, I want to determine the local extrema of f of x equals x squared minus 64 all to the power of 2/3 as well as where they occur. So again, we want the domain of this. The domain of this function is all real numbers. It's not immediately obvious why that's the case, but here's the reason why. What we're doing here, when we take a rational exponent, this is the same thing as the cube root of x squared minus 64 squared. Cube root functions, you can plug in positives, you can plug in negatives, you can plug in 0. It's always defined because the index is odd. But even if it weren't odd, even if it were even, I'm raising this to an even power, so the thing in the radical, the radicand is what we call that, is always positive anyways. So this is going to be defined no matter what I plug in for x. Okay, so our domain is all real numbers. Now we want to start looking at the derivative. F prime of x. What can I say about f prime of x? Well, I need to use the chain rule. So the power 2/3 will come down, 2/3. Then I have x squared minus 64. I subtract 1 from my exponent, so I get negative 1/3. And then I multiply by the derivative of the function on the inside. That's my chain rule. That's 2x. Let's simplify that a little bit. So 2x times 2/3 is 4x over 3. But let's take the 4x and put it up there, and the 3 and put it down here, because now I'm going to use my negative exponent to write this as x squared minus 64 to the 1/3 power. Okay? I can do one more little thing to help with this. 4x over. I noticed that x squared minus 64 is a difference of squares, so I could write this way. Let's use the cube root. 1/3 power is the same thing as cube root. X plus 8 times x minus 8. Since x squared minus 64 is a difference of squares, that's how it factors. Okay? And this is my derivative. I use this to find critical values in two different ways. I find where this is equal to 0, and that only happens when my numerator is equal to 0. That would imply that x is equal to 0. Okay? Or where f prime doesn't exist. So it doesn't exist at x equals plus or minus 8. Because whether I have a positive 8 or a negative 8, if I put that into this expression here, I have the cube root of 0, which is 0, and now I am dividing by 0. So if x is equal to plus or minus 8, the derivative is not defined. However, both plus and minus 8 are in the domain of the original function. It's only the derivative where that's a problem. So now we have those other types of critical values that we said could occur. So here's my critical values. My critical values are x equals 0 or plus or minus 8. So I need to put all three of those on a sign chart. Negative 8, 0, 8. They have to be in order from smallest to biggest, right? Let's see what happens with our derivative when I plug different test points in. I have 4 subintervals to worry about now. So let's pick something that's way over here, like x equals negative 100. If I plug that into my derivative, my numerator will be negative. 4 times a negative number, right? That's negative. In my denominator, this 3 is always positive. It's not really doing anything. The negative 100, if I plug a negative 100 in for this x as well as this x, both sets of parentheses come out to a negative number. So negative times negative is now positive. The cube root of a positive number is positive. My whole denominator comes out positive. So what I have is negative over positive, which is negative. F prime is negative. Notice at no point in that process was I really worrying exactly about what negative 100 plus 8 was, or negative 100 minus 8, or the product of those, or the cube root of that. You know, that's a lot of extra work that you don't need to worry about. We only care about whether the whole thing comes out positive or negative. Now let's pick a test point over here. Say x equals negative 1. That's in between negative 8 and 0. If I plug a negative 1 in for this x, I get a positive here. If I plug it in for this x, I get a negative here. Positive times negative is negative. Cube root of negative is negative. Times a positive 3, still negative. But if I plug in negative 1 in up here, I also have a negative in my numerator. So now I have negative over negative, which is positive. F prime is positive. Okay, same idea, but this time let's use x equals 1 because that gives us a test point between 0 and 8. If I plug a 1 in, positive in my numerator, positive here, negative here. If you go through the steps and verify, you will get a negative derivative there. Finally, let's plug in some really large negative or positive numbers, say 10,000. Doesn't matter. Well, in all cases, every factor in this thing is going to come out positive, so the whole derivative would have to be positive in that case. Okay? So what does this mean? Well, from here to here, I have f prime is negative, and then it switches to being positive. So we're going to go from decreasing to increasing. Notice the way that I drew that. I made a cusp instead of a nice kind of like valley there. And that's because I know that the function is not differentiable at -8. We found that up here. So the graph would actually have a cusp. You don't need to draw it that way. It's just, I'm trying to be a little more accurate. Our function is defined at 0, as is its derivative, and we go from a positive derivative to a negative derivative. We go from increasing to decreasing there. And then here, we see the same sign change that we saw over here. We go from negative to positive, decreasing to increasing. Okay? So, what does this tell me? By my first derivative test, where we saw these sign changes, f has a local maximum, the only place where that occurred was here, of what? At 0. So plug 0 in, not into the derivative, but the original function. If I plug a 0 in here, I have 0 squared minus 64 to the 2/3 power. Let's work that out. What is f of 0? So it's negative 64 to the 2/3 power. Now that might initially seem really difficult to work out until you notice that negative 64 is actually just negative 4 cubed. So really negative 4 cubed to the 2/3 power. Now I can multiply these exponents together to get negative 4 squared, which is positive 16. So f has a local maximum of 16 at x equals 0. F has local minima of, now notice I'm using the plural because we have 2 places where a minimum value occurs. Minima of what? Well, it's plus or minus 8. That's where it occurs. So at x equals plus or minus 8. But notice if I go up to the original function, whether I plug a positive 8 or a negative 8 into this, I'm squaring it, so I'll get the same thing in either example. F of plus or minus 8 is equal to positive or negative 8 squared minus 64 to the 2/3 power. Whether it's positive 8 or negative 8, when I square it, I get 64. So 64 minus 64 is 0, and 0 to any power is still 0. So I get local minima of 0 at plus or minus 8. And that would be my answer to that one. All right, this video has gone on a little bit too long, so we're going to stop this one here.